Hello, good evening, everyone. My name is Edward Chang, and my presentation title is The Future of AI from Unconscious Models to Conscious Reasoning, and then leading to emotional intelligence. And what happened in the AI community in the last 6 months? Pretty much everyone is talking about ChatGPT and the large language models. And now we consider other modality of data, and we're expanding the focus from just language to foundation models, covering multilingual and also multimodality. And what happened in the last 10 years to lead to this large foundation model paradigm? So about 12 years ago, ImageNet was made available for computer vision researchers to do competition. And then the community found out using the data-driven approach, which allows an algorithm like CNN to learn features from data, the performance is much better than human engineering features. And this leads to the large-scale computation capacity requirements. And NVIDIA was extremely successful because it's a GPU offering. And the natural language processing community was kind of lagging for about a couple of years until 2014, when word-to-vec, word embedding, was invented by Google. The cinema problem was partially solved. And then the transformer using this attention mechanism was developed by 2017. And the significance of these transformers is to address the issue of polysemy. And in the linguistic field, since about 17 years ago, an important theory is saying, if we want to resolve the meaning of a word, you have to look into its neighbors. And the concept is very straightforward. However, it took until 2017 when transformers become available to finally computation model is able to kind of modify polysemy successfully. So this a simple example at the bottom of the screen shows the same word bank in different contexts, right? The upper one, the nearest neighbor word is river, and that means it's a kind of a wall along the river. And the second one, making a deposit to a bank, then deposit signify the bank is a commercial bank. So we have to kind of paying attention to the nearest neighbor words. And the example here is a pronoun resolution. We need to resolve the pronoun it, and there are two nouns in front of the pronoun, and it could be animal and could be street. And after transformer has trained using large volume of data, then this attention model is able to weight animal higher than the street. So the darker the color means the weight of the particular word is heavier. And the heavier one with higher probability will be considered to be replacing the pronoun it. So because of these findings, and also because of data-driven approach, the AI community started to have these larger and larger models. Indeed, GPT-3 launched about 2-3 years ago. It's about 175 billion parameters. And then DeepMind as Rachel is coming pretty much getting to this arms race situation. And about a year ago, people rumor GPT-4 may have more than 10 trillion parameters. But however, GPT-4 after its launch, although the internal architecture was kept kind of confidential, and eventually the fact about GPT-4 has about 1.7 trillion parameters was recently disclosed. So let's look at GPT-3 and progress to GPT-4. So GPT-3 has 175 billion, as we just mentioned. And in the paper I just put online yesterday, and we first of all discussed GPT-4 is actually an ensemble model. GPT-4 has 8 submodels. Each submodel is about 220 billion parameters, the GPT-3 size. So it did not increase the size of GPT-3 to have 10 times or 100 times the parameters. Rather, GPT-4 elected to expand the model horizontally. So this gave us probably a couple of hints. One is perhaps further increasing the number of layers in the transformer models may not be very useful. And there were a couple of research results already indicating, for example, in the BERT visualization, the researcher found out not all the attention heads were actually useful in the final prediction. Only about 10% of the attention heads have values in there. So this is already kind of showing that although we have large number of parameters, some parameters may not be useful or will not be used at all. And also from the perspective of Shannon limit, right? This is a compression limit. And given a set of documents and using lossless compression as an application to think about this compression ratio, there has to be a bound somewhere. So we believe GPT-3 may have run into the bound. So therefore, adding additional layers may not be extremely helpful, but just wasting a lot of computational power. So instead, having 8 members take advantage of statistical redundancy can improve the robustness of the system. And this is well established since the bagging methods inception in 1998. So the context window is another thing enhanced by GPT-4. And this context window was quite contrived or constrained in GPT-3, only about 4,000. So we talk about attention, right? If the window is too small and the word you want to have resolution is really out of window, the references, then the resolution cannot be performed effectively. And GPT-4 increased it to 32K through a very clever data scheduling algorithm. So it actually did not increase the memory requirement so much. So this was a kind of a system level breakthrough. So with an ensemble of committee, which can improving robustness of the system, and also with a much larger context window, which can perform much better information resolution, and GPT-4 was very successful. So this picture shows GPT-3 is just one robot, and GPT-4 has an army of submodels. Each one is equivalent to GPT-3. And a couple of questions here related to the design issues. One is how many submodels is desirable? 8, 16, or even more? We know Google's latest model used 64 submodels. And number 2 is the submodel, how strong the submodel should be, right? A submodel can be much smaller than GPT-3, but that will mean every submodel is weak and erroneous, and it may not be able to produce good results. An analogy is if you make every submodel, their intelligence level is like kindergarten. Even you put into 64, 128, the aggregate decision may not be good. So it's a design kind of trade-off. The mode will be more expensive, but the larger a submodel, then probably you don't need to have too many members. And the second issue is about how do we partition the training data? And I have some in-depth discussion in the paper. So because of the limitation of time, we will not get into there. And as shown by benchmarks conducted by Microsoft, GPT-4 clearly outperforms GPT-3 and its competing offers. And again, thanks to its pretty wonderful architecture. So we'd like to gain some insights in the remainder of the talk, right? When you want to design additional features or remedies the current shortcomings, with the understanding of the design insights, then we can have the accurate and effective remedies. So the first question is about generative AI and distributed AI. What are the differences between the two? And we can take a look at the architecture of Google and the GPT launched last year. And both Google Search and ChatGPT, they have all the data in the world they want to access. In fact, I consider Google may have even more data. And Google then index those data and ranking the content. And Google for sure has its own foundation model. The early model is BERT. And then they put the Google interface on the top. And OpenAI ChatGPT, similarly, it has a foundation model to generate content. And its foundation model right now is GPT-4, and then fine-tuning ChatGPT to remove toxicity. So you look at architecture, they are very similar, but at the same time, there are some very subtle differences. And the BERT is a model predicting missing words with context. And GPT is predicting the next word with context. The difference is a little bit subtle. I would talk about maybe the mental differences in the next slide. But let's look at the similarity. Both BERT and the GPT, they resolve synonyms and polysemies using the same mechanism developed by Google, word-to-vector embedding and the attention model. So the only difference is one is to fill the blank, guess or recover the missing word, and the other one is predicting the next word. We look at in education, right? Suppose, especially in Asian countries, we like to exam students having this kind of question of fill out the missing words. So if you have an article of 100 words, and the teacher may mask a few words, ask student to fill in those missing words. And this kind of training or learning may not be able to foster creativity. On the other hand, writing an essay is totally different. So writing an essay is generating one token after another one. So we think about when we do this kind of fill in the blank, it is really hard to hallucinate, right? So example, we just shown, suppose the first one is say, my birthday is December or September. And this missing word is a proposition. Very, very constrained. And also during the training, it requires to minimize cross entropy error and requires to fill in the exact same word got taken out. That was extremely constrained because when you look at all those common sentences, replacing a word with a synonym or other expressions may still have a very fluent sentence. So writing an essay provides this kind of flexibility, but not really filling the blank. And we really cannot examine which one is more flexible just by looking at the transformer code or the objective function. But let's look at this mental iceberg put forth by Freud. So Freud basically saying, well, we have 3 different states of our mind. At the bottom, unconsciousness. In the middle, maybe subconscious. On the top is consciousness. And consciousness operates kind of reasoning and conduct planning. And unconsciousness operates all the reflexive kind of activities, including heartbeat, metabolism, and so on and so forth. And memory is in the middle. So now if we plot the 2 tasks, fill in the blank, and the generative model, then they are in different quadrants in this picture. So this is, I call intelligence landscape. On the axis is the computation intensity. On the left-hand side is low and right-hand side is high. And on the y-axis, on the top is consciousness, at the bottom is unconsciousness. And discriminative AI, like classification, belongs to low in computation. For example, the fill in the blank example, and we illustrated, it's sort of like a memory problem, right? So maybe you need to come to the consciousness to find some indexes, then you go back to retrieve in memory about the answers. But it's not really a highly conscious kind of operation. On the other hand, generative model is different. When we write essay, we cannot write essay when we are in sleep. We have to be highly conscious, aware of the situations, also interact with the memory, and to be able to accomplish creative writing. So by looking at this graph, it seems to hint that the BERT model was not extremely successful, and Google actually changed the objective function to also guessing the next word. So now they are both on the same direction. So this is one kind of warm-up heuristic. And the next one is alignment. So we heard about the complaints on ChatGPT, and some saying, well, ChatGPT may have a person living it, and the content it generates may have toxic language and could be biased. And hallucination is another complaint. And my own experience is when you suggest ChatGPT to provide references, some suggested papers may not exist. And also some folks are really worried about human extinction scenarios. So there has been 2 efforts performed by the OpenAI company. And first one, they do this reinforcement learning with human feedback. And the next picture shows a training pipeline of this foundation model. data collection, data generation, training, adaptation. And eventually, when ChatGPT has been deployed and OpenAI hires some raters and to try to rate the output generated by ChatGPT, if the output is not desirable or desirable, then the information will be fed back to this fine-tuning process. And the parameters in this foundation model will be altered. Okay. So then the question is, should we do this alignment before we started training or after the training has completed? And OpenAI did it using this post-alignment kind of paradigm. And post-alignment, yes, it's good. It can reduce toxicity to a certain degree, but it's really not so desirable because OpenAI can only put forth one set of rules and everyone else has to follow, right? So it cannot be able to customize to different cultures and the different individuals. And also another bad thing is the kind of technical problem. So once you have fine-tuned for the purpose of removing toxicity and other tests, the performance of other tests, for example, especially in coding, the performance drops substantially. And many coders complaining, if you ask GPT-4 to do coding through API, the code quality is good, decent. But if you go through ChatGPT to ask ChatGPT to do coding for you and then call GPT-4, and the coding quality is compromised. Okay. So in real life, you can consider if a person is very creative, but the family member is saying, well, you are really great, but if you can clean up your desk every morning, you'll be a better kid. And you can consider if that particular kid start to pay a lot of attention to cleanliness, and maybe creativity will be reduced. So we perhaps need to just take our children as the entire package rather than micromanaging them to shift their attention from one place to the other. Okay. And pre-alignment is perform censorship before we conduct training, basically going into the training data to see which is good, which is bad, and removing all the undesirable content. And the good thing is, yeah, the tyrant may feel so good, everything is under control. But the bad thing is that this process is very, very subjective. And once you have removed certain content, and the content may be tolerable in the future generations, but the knowledge was lost because of this kind of brutality. And even worse, most ugly, as I documented in the paper, is if you remove, let's say, negative information, and when you try to build a classifier, and suppose this is a binary classifier, you want to have positive instances and the negative instances. Suppose all the negative instances have been removed, then it's impossible to draw the boundary around the positive ones because you can draw it very, very loose, and the validation sets will still say your classification accuracy is right. But when you get into the real world situation, when some unseen data, which was negative but get removed, the classifier is not going to be able to discern it. So in fact, when you perform this kind of pre-censorship, the classification quality is degraded, and the information you really want to screen in the first hand cannot be conducted by the model you have trained. So this is really kind of ironic. So we know there are some countries still trying to make sure the censorship works. But however, the effectiveness of their model is compromised. Perhaps they have no idea what has been going wrong. So the paper provides some more interesting insights, and you can take a look into our arguments. So let's come back to look at this mental iceberg. And alignment basically is definitely in the conscious situation. So while we show this picture, it will become evident in about 4 or 5 slides. The next idea is called polydisciplinary. And this term was mentioned by Eric Horvitz. He's the CSO of Microsoft. We know Microsoft and the OpenAI, they have been working together to benchmark OpenAI's GPT-4. And OpenAI has kept everything in confidential, so Microsoft people can only kind of observe from outside or conducting performance evaluation using APIs. But Eric's reaction was, well, he considered GPT-4 to be polydisciplinary. And this term is different from multidisciplinary or interdisciplinary. So polydisciplinary focus, the emphasis is a person has multiple PhDs, right? And not only he or she has multiple PhDs, and the knowledge has no boundary. So the department, when we came to university to select our majors, the majors are really kind of artificial to give us excuses not to study too much. But in the real world, there shouldn't be boundaries between knowledge. So you look at how GPT-4 was trained, we have a large set of documents input to GPT-4. We have never told GPT-4 to say, this is a set of documents belong to physics, and those are for economics, right? So GPT-4 just lump everything together. So the features it learns and the heuristic and knowledge it possesses is polydisciplinary. And this is very critical because when we answer a question today, suppose we know a question is from the physics kind of domain, we answer using physics knowledge. But the most effective answer should be just cross-disciplinary. And GPT-4 is able to do that, but human is not able to do it. So this comes back to when people talk about hallucination. So what hallucination is about? So we can say, can DAI hallucinate, right? So we talk about this fill in the blank. It's unlikely because the training process was very constrained. And GAI would hallucinate, but is that a problem or it's the nature of writing an essay? Right? If you ask me to write an essay, yeah, I will definitely hallucinate. So complaining GAI hallucinates, I think it's a little bit pointless. Of course, I understand when you try to generate law cases or technical reports, you don't want to kind of falsify titles or authors, but those can be remedied using other methods instead of fixing hallucination in the GAI model itself. And we talk about it in about 5 slides. So hallucination is really talking nonsense. And once you have touched upon this polydisciplinary idea, then maybe GPT-4 is not really providing nonsense. GPT-4 at some time maybe give us some information which we just don't know. So there are a lot of information in the world. It's called unknown unknowns. We don't even know their existence, and there's no way we can even ask questions about those unknown information. And people also complaining GPT may not be able to follow human common sense. So this is another kind of ridiculous complaint, because common sense, in a way, is kind of human knowledge. And if we do not input human knowledge into the training data, of course, GPT cannot have common sense. So this kind of problem can be easily fixed by interacting with users to collect even more training data. So reducing hallucination. Okay, if we want to confront the problem directly, we want to see what exactly the source of the problem. And can we just by adding more parameters to solve the problem? The answer is probably not. And there has been some a thorough empirical study performed, which I will show in the next 2 slides. Diversity of training data is essential to solve this problem. And another method to solve the problem is using ensemble, right? This is precisely what GPT-4 has been doing, having these 8 submodels. They try to make a decision in the committee. It's like reducing the same mistakes from multiple people. So when we talk about large language model, what is large? Yes, the size of document is large, but that's not what we are talking about when we talk about the large number of parameters. When we talk about large number of parameters, we are referring to the transformer model. How many attention heads we have, and how many hidden states we have, and how many layers of the attention layers. So we look at the picture on the left-hand side. There are 3 parameters beside the number of parameters in this foundation model. W stands for hidden states. Pretty much it's about 5,000 or 50,000 in GPT-3. And number of attention heads could be ranging from 40 to 80. And already researchers complaining the number of heads may be already too many. And depth, and heuristically, we know eventually adding more depth will not be able to increase accuracy because it's kind of diminishing return. And we can examine actually the layers by look at whether adding additional layers, those additional layers, the values in those layers will be modified. If we reach kind of steady state, even let's say we put into thousands of layers, we can easily do compression afterwards, okay? So size matters, that's true. but size may be able to improve accuracy, but not really robustness. And for robustness, a professor at UW, Louis Schmidt, did an extremely thorough and impressive empirical study. And basically, he and his team collected all the image classification models and the testing data. So there are 213 testing conditions, and there are more than 200 different models using ImageNet. So what he was trying to do is, first of all, trying to verify, is it true with more parameters, the accuracy of the model will be better. And this is actually indeed, not surprisingly, it's okay. So this picture is a little bit challenging to interpret. Let's spend some time to explain it. On the x-axis, it shows the accuracy of this kind of top 1%. On the y-axis, it's exactly the same as the x-axis. So why this x and y we want to plot these two dimensions? Suppose we're changing the testing condition a little bit. If the system is extremely robust, then the accuracy plot on the x and the y axis both should be the same, right? Suppose I have a picture, a panda picture. I alter a couple of pixels. When I classify this picture, still it should be panda if the robustness is good. So therefore, accuracy should not be different between x and y axis. But if the robustness is not good, then after changing the testing condition, the performance will degrade. And indeed, if you look at this picture, the robustness gap is about more than 10%. It means despite which models we have used, and despite the number of parameters in each model, and the image processing or in the computer vision area, the robustness is just not there, right? This is really kind of surprising. At the same time, is sad. And according to Andrew Ng, he had a kind of interview conducted 2 years ago, and he said his experience with medical images were the following. He can classify to detect lung cancers, for example, using Stanford's data. Then applying the same classifier in a different hospital, the accuracy would drop by 10 to 20%. This is precisely what this picture is showing. So therefore, radiologists still, they have not lost their jobs, because fundamentally, the robustness problem has not been solved in the computer vision area. And what really can address the problem? One way is doing data augmentation. You try to impute a lot of kind of synthesized data, right? Trying to put arrows into the testing data and trying to put those data into training data to try to kind of artificially synthesize robustness. But there's only limited augmentation you can do, and the augmentation increases the number of training data, and in turn, that will cause the training time to be much, much longer. So typically, this is not a method people would like to employ. So what is the only remedy? So according to the UW's experiments, the only remedy seems to be increasing the amount of training data diversity, not only the volume, but also diversity. So the 3 dots showing here is on, for example, Instagram 1 billion data added to a particular model, but Instagram smart images is very diverse. So the robustness, the accuracy, you look at the dots, green dot, can be plotted higher than the other models. This means the robustness gap is shrunk, but still substantially big, like 10% instead of 12 or 13%. The conclusion is, in NLP area, they also conducted experiment, the similar results happens. So the conclusion here is the more data with diversity variety can improve robustness. And also the size of a model, as we mentioned in the beginning, has a theoretical bound, like Shannon limit. And why we talk about all of this? And this is, again, related back to the new architecture done by GPT-4, right? If we consider robustness is very critical, and it requires a set of diversified images or data, then when we design the ensemble models for GPT-4, we have to consider 2 things. One is, for each submodel, we need to make sure diversity is still there. So subsampling too much will be detrimental, right? And also, we don't want the submodel to be too small. As we mentioned, we don't want the submodel to be very weak. So therefore, the sampling method, sampling algorithm, to sample from the original training data for each member model is a very critical decision to make. And I have no time to talk about details, but again, please visit the paper I just put on the internet yesterday. It actually has some interesting discussions on how to conduct sampling. So therefore, the members of GPT-4 can be both robust and also be able to achieve statistical redundancy. So the next topic is about computational consciousness. With the remaining time, I'd like to motivate why we want to get into this discussion. Because a lot of people are saying, well, GPT-4 cannot do reasoning really well. And then they're complaining about the problem is actually within the foundational model. And I really do not consider so. And again, let's look at this picture we discussed so far. A lot of problems or features in GPT-4 are really in the consciousness domain. So if the foundation model has no notion of consciousness, and how can reasoning or empathy or emotional intelligence ethics be modeled? Impossible. So let's go back to look at this Yoshio Banjo's keynote conducted about 4 years ago. He said, well, the current AI has run into some limitations, including robustness problem, as we just mentioned, and interpretability problem, and it couldn't do reasoning. Okay, and this is again true for the foundation models. And Banjo proposed the fix may be developing system 2 on top of system 1. And at the same time, there are a couple of Nobel laureates also suggesting we have to build conscious layer on top of unconscious layer. And the foundation model can be characterized as an unconscious layer, and the conscious layer has to be developed on top of it. And this is a paper I put forth about 3 months ago, talk about our architecture of modeling human consciousness. And briefly, the consciousness of an organism can be defined as the organism's orientation and interactions in a 3D Cartesian space and also with time. And we don't want to say which organism has consciousness, but as a whole, we say, well, everything has consciousness, but the complexity of consciousness depends on the amount of information the organism can collect and need to process. And in this regard, the human has a very complicated set of sensors, and we have a huge amount of data need to be processed. So therefore, our consciousness is highly complex. The second way to think about the problem, how to tackle the problem, is when we try to model consciousness, we don't have to follow the human neuron structure. First of all, we don't really understand human brain so well. So secondly, we can just follow the functionalism's approach, which basically we can model the essential functions of consciousness rather than we have to mimic the physical appearances of functions of consciousness. So there are some key functions only when we are in the conscious mode we can conduct, like learning, decision-making, creative planning, reasoning, and so on and so forth. And you can look into the paper to see how we model the transition between consciousness and unconsciousness. And from unconscious to consciousness, we use the Schrödinger's quantum jump. And the other way, and you can characterize it by using the second law of thermodynamics. And this is not critical, but why we put forth the implementation is because we just want to show it's feasible, it's possible to implement consciousness in a computational framework. Okay. So this is a very simple example to show how this consciousness and consciousness, how do they interact. So when we get into the conscious mode, because we have to learn something to adapt to the environment. For example, when we learn walking, biking as a child, and the first time you come to Paris, you are not familiar with the street. So therefore, when we go to any places, we need to query other people or we need to navigate with a map. But when we are so familiar with the situation, let's say walking become habitual and the action become repetitive, then this whole thing get returned into our unconsciousness, right? Everything become reflexive. So we walk to the classroom, we drive in Paris, back to school. If we really become routine, these are kind of reflexive, habitual. Only until, let's say, on the street, we run into an unexpected pedestrian, then now we are awakened we say, well, we have to adapt to this novel situation, and consciousness has to do planning and to kind of activate our muscles to try to deal with the unexpected situation, reducing hazards. And this is sort of the modules of our COCOMO model. But the critical thing I want to emphasize here is we model critical thinking, and we are also able to model emotion and behavior modeling in COCOMO. And so let's briefly talk about critical thinking. Critical thinking, again, cannot be a part of your foundation model. Think about it. The foundation model only deals with two things. One is how to address word embedding similarity, and the other thing is this polysemy, right? And the optimization function is try to minimize cost entropy errors. So where in the word your foundation model can suddenly start to conduct reasoning. So we have to just build another layer on top. And I consider the following proposal to be probably the best. I kind of present to many places, but so far it seems to be bulletproof. So we say it's called Socratic method. So this is another paper. So Socrates is saying, well, I don't know. What I know is I don't know everything. So Socrates learned something by having a dialogue with his students. And this is different from the traditional Asian method. Confucius pretty much top-down teach students a lot of things. But Socrates is through a dialogue process to understand or acquiring knowledge. So the Socratic method has some sub-methods. And this, for example, including definition, generalization, induction, encompasses, hypothesis elimination. And so just for because of a shortage of time, assuming there are certain templates offered by the Socratic method. And then we say, okay, that's really great. And suppose there are several methods we like to employ, but those are not really kind of solid. Those are kind of fluffy. So we like to map these Socratic methods to formal reasonings. There are just three reasoning methods: inductive, deductive, and abductive. So this picture shows the design flow. So once you have utilized one of Socratic template, then you can map the template to either inductive reasoning, deductive reasoning, or abductive reasoning. And each of the reasoning methods behind it, there are machine learning or statistical tools to support programming. And this process is really robust. And you can do this by conducting critical reading, critical thinking. And we have proposed a subroutine called CRIT, and which would extract conclusion of an article, then extracting arguments from the article, evaluate the validity and the credibility of each argument, and assess counter-argument, eventually give a total score. And this kind of subroutine can be easily crafted based on your situation or desirable functionalities, and it can be utilized to verify truth. Okay, and so therefore you have to really build reasoning modules on top of your foundation model rather than the other way. So the details, please look in the paper. I'm going to skip forward. The final topic we kind of talk about is emotion. So how do we model emotion rather than saying using this kind of reinforcement feedback situation? If we can model emotion within the model, and this is internal rather than external forces, then it's easier to customize emotion and behaviors. And this could be done by showing example behaviors and example emotion to ChatGPT. And at Stanford, we developed this system called Nura to try to teach autistic children how to speak empathetically. So basically, we speak to ChatGPT and give ChatGPT a large number of examples, appropriate responses, inappropriate responses, and so on and so forth. And every individual has their subjective kind of happiness or unhappiness. So individual can convey their positive and negative to ChatGPT. And whenever ChatGPT needs to talk to that particular person, it can just load the contextual information of that person, then it will behave accordingly. Okay, so if you have you're interested, you can do some experiment on the site. Okay. And when we want to build a senior care agent, not only it has to have medical knowledge, but when we survey nursing home, and they are requiring certain caring behavior, and those can be quantified as attentive listening, empathetic patients, so on and so forth. And again, those behaviors can be conveyed to ChatGPT through a set of behavior examples. And then your agent will be able to customize and behave according to individual definition of ethics. To summarize today's presentation, we talk about the capabilities and insights of GPT-4, and not only we enumerate insights, but also point out some shortcomings. And we use computational consciousness to try to remedy those shortcomings, and including reasoning and model subjective emotion intelligence. And there are much work to be done in the future, and I have no time to convey all details, but I'll provide a list of reference, and you can be in contact with me if you have any further questions. Thank you so much for your attention.